What's going on, everybody? Well, you've had a chance to explore the normal distribution for a little while and its strengths in being able to represent individual pieces of data and describe how they're distributed from smallest to largest around their mean. But oftentimes in statistics, we're not dealing with individual pieces of data. We're dealing with sets of data. We're dealing with samples of data, samples of 10, samples of 20, samples of 100. And if we, for example, take a population of data, that even one that we know how it's distributed, and we take samples out of it of a certain size. We take a bunch of samples out of it and we average that and get an average. And then we take some more samples and then we average those samples out and record what that is. We take some more samples, we average those and record that. We take a few more samples, we average those and record that. What kind of a distribution are we going to get of those averages? Here's where we start to deal with something called the central limit theorem. It's what we're going to be exploring today, but first let's take some time to focus on our breathing, to take some time for ourselves. This is a time in which we can take advantage of the fact that you are in a place right now, especially in a time such as this, where this is a time that can feel very, very boring. It's a time in which you can feel isolated, but it's actually a time, if you're willing to do exercises similar to this, in which you can get in touch with yourself. And what I mean by that is that you can get in touch with what it is that you are, who it is that you are, apart from the expectations that I might have, that your parents might have, that other institutions might have. It's a chance for you to find out who you are and to ask yourself some questions about what you should do, what values you should have. These are questions that you can answer if you will just allow yourself to be quiet and to listen to yourself. How will you know that you're actually getting the true stuff from within? Simple. You'll be able to tell when you're calm, at peace, passive, when you're seeing yourself not fighting against the rest of the world, but feeling a sense of connection to the entire world, feeling a sense of oneness with the world. This is something that you can get by simply doing these kinds of exercises for extended periods of times. Now, for today, we're not going to be able to get you that far with just a couple of minutes of doing this, but we can get you to the point where we are getting ourselves focused for what's coming next here. But this is a skill that I'd want you to cultivate. So take some time and focus on your breathing. See if you can feel that your body is alive. Become very, very alert to your surroundings. Basically, empty your mind and enter awareness. Take some time for that. Welcome back. Well, let's begin this process of taking a look at what sample means look like when we start to plot them. Let's go over to this screen here, and if I've got a population of people here, I can ask myself the question, what is the mean resting heart rate of this population? That's a very, very large population to sample to find out all the information here. It's conceivable that it could be done, and certainly there is an average heart rate that exists for all of these people. Realistically, what's going to happen is we're going to take a sample out of these out of this population, and much like what you did with the M&Ms in class, infer what the population is of this, what the heart rate is for this population based on the average heart rate of this sample. And so let's say, for example, the average heart rate of this sample is 74. And perhaps that 74 is exactly the same as the average heart rate of this population. Maybe it's a little bit smaller, maybe it's a little bit larger, but we can describe the difference between the mean of this sample and the population mean, which is usually unknown. We don't really know what it is, but we can certainly theorize that there is a difference between this mean and the population mean. They're probably at least a little different, and that difference is something that we call the sampling error. So in reality, let's talk about what we might do here. We've got the same population, and it's distributed in a, let's say, in a normal distribution. And we take multiple samples out of this. These are different people, different samples that are made out of this population, and we get different sample averages for each one of these. What are these averages going to be like? And how are they going to be distributed? Well, here's where we can start to take a look at some examples here from actual simulated data here. What I want to do is to get out of the presentation here very quickly and to show you something that I made here. This is an Excel spreadsheet, and here's what this Excel spreadsheet has. It's similar to the Google Sheets that you have here, but I'm actually to the left here. I've got 10 columns. Each column shows 100,000 random data values, each one of them between 0 and 100. So for a total of 1 million data values, each one between 0 and 100. And what I'm going to do is to ask the program to just generate 100,000 random numbers, and it's going to pull out 100,000 of each. Actually, I should say it's going to randomly pull out 100,000 of these data points here, and it's going to find out what the distribution of those data values are. And so I can do that actually by calling up, this is something called a macro, and you'll be able to watch it running here. You can see it's pulled up 1,400, 1,900, 2,000, 3,000. It's going to go to 100,000 here. So it's going to be working on this for a little bit here. While it's doing that, let me just reiterate what it's doing is it's pulling 100,000 of these values out of this population here. We're assuming this population is 1 million values in size. And you're going to see here what the distribution is of these values that it's pulling out. We're now up to 19,000 out of 100,000. So you can actually watch this here. It's pretty cool. This makes use of something called Visual Basic for applications. It's an add-on programming software that comes really with every element of Microsoft Office, be it Microsoft Word, Microsoft Excel, Microsoft PowerPoint, Microsoft Access, Microsoft Publisher. All of these things have this additional add-on here, and I'll actually show in a companion video for those of you who are interested exactly how that macro works. But it's pretty cool. I mean, it allows for you to do some things in Excel and PowerPoint and Word that even some of the most experienced Microsoft Office users don't know how to do. It would definitely give you an edge in the marketplace. We're now past the halfway point here at 53,000. So we're just going to wait here for a little bit longer for it to finish out all of these here. When this is done, it's going to show all the values that it pulled out here. Then using this, it's going to generate a histogram of what those values look like. It's going to calculate the mean as well as the standard deviation of all of those values that it gets here. We're now up to 2/3 of the data that it's pulled up here. This is pretty cool how it's able to do this pretty rapidly. And we're about 3/4 done. %. I'll also have this spreadsheet available to you on D2L, so you'll be able to download it and try this stuff yourself. All right, 90,000 points. And here we go. All right, it's done. It's going to record all of those numbers here in this column. Then it's going to go ahead and generate its histogram of what it found. And when it's done, it's going to plot it up here. There we go. Here's the histogram going. And here's what it looks like. Has a mean of 50. Well, that makes sense. It's 100 numbers, well, a million numbers, each one of them from 0 to 100. So it makes sense that the mean is going to be 50. You can see what the standard deviation is here. So this is very, very much like when you were rolling a single die and you wanted to create a histogram of what it looks like, what the probability distribution is for rolling a single die. If you rolled a die 60 times, you'd have something close to 10 1s, 10 2s, 10 3s, 10 4s, 10 5s, and 10 6s. You'd have pretty much a flat distribution, and that's precisely what you see above me here, this kind of a flat distribution. Not exactly flat. There's a little bit of randomness that's going into this, but it's basically flat. Well, what happens if I ask it to not just pull one sample out, but to pull out two samples, average them, and then record that average? How does this change? Well, let's try that. I'm going to change this from 1 to 2, and then I'm going to rerun this macro here. There we go. So it's running right now again. It's making use of these million data values here. It's pulling out 2 at a time, averaging them, then recording that average. Pulling out another 2, averaging them, recording that average. So think about to yourself, how common will it be for us to get an average really close to 0 or 1? Well, there are 0s and 1s somewhere in this chart to the left here, all these data, but if it pulls out a 0 and a 1, chances are it's going to be also pulling out something that's not a 0 and a 1. It's a value that's much bigger than that, and once that averages out with the 0 or the 1, then it's going to be something, the average is going to be something larger than a 0 and the 1. And so in reality, it's going to become a little bit more rare for us to get numbers that are really small. In the same way, if it pulls out a 99 or 100, chances are for its second value, it's going to be pulling out something that's slightly less, somewhat less than 99 or 100, and that's going to make it so the average is also less than 99 or 100. And so the incidences of these averages, these values here close to 99 or 100, they're going to still happen, but not nearly as often as it's going to happen that you see stuff around the central values. You're going to see a lot more instances of things that are near the center. We are now over halfway done with this. And so think about what this was like when you were rolling 2 dice. We've actually covered that many times. What does it look like when you total the value of 2 dice? What does that probability distribution look like? As you recall, you'll see this. You can see this also in that animation video that I made not too long ago. If you recall, that creates a pyramid type shape here, and I bet we're going to see something like that here when we run this analysis here. We're now about 3/4 of the way done, so let's watch the rest of this here. 80%. So it's randomly selecting 200,000 of these things now, 100,000 pairs, and averaging each pair. And it's going to be recording that here. We're at 91% done. %95 done. Okay, and it just finished there, and it's going through and it's copying all those data data values down. Then it's going to create our histogram. Yeah, it's working on that right now. And that's going to calculate the mean and the standard deviation here. There it is. There's that pyramid shape that you saw before. Now ask yourself the question here, has the mean changed with this analysis here, or is the mean still pretty much around 50 or so? Well, you can surmise it from the shape here. You can also see it from the data here. The mean is once again pretty close to 50, slightly less, slightly more. That's some little randomness that comes into play here. But also ask yourself, is the standard deviation going to be larger or smaller? Hopefully you can see that because this distribution is more compact, it's a little bit more together than it is apart, that this standard deviation is going to be slightly smaller, and it is. Let's try to see what we get if I increase this now to 5. So now when I run this, now it's randomly collecting 5 samples, averaging them, randomly collecting another 5 samples, averaging those, randomly collecting another 5 samples, averaging those, and so on and so forth. So 500,000 samples in total is what it's grabbing here, 100,000 groups of 5. And in reality, because of that, the entire data set is only 1 million data values. So if we're grabbing 500,000, it's actually pretty likely that in some instances we're picking up data values that we picked up before. We're sampling with replacement. In other words, after we sample something, we don't disqualify it from being pulled out again. It's like we're fishing and we're throwing the fish back. So it's quite possible that some things are being sampled twice, but that's okay. We are up to about 1/3 of the way done here. So think what this was like when you were watching that animated video here, and we went from adding 2 dice together to then adding 3 dice. How did the shape of the distribution change? Is it going to stay a pyramid shape, or is it going to change to something else here? So we're now getting pretty close to the halfway point. Also ask yourself, what's going to be the changes to the mean? What are the changes going to be to the standard deviation when this happens here? Okay, about 62% done here now, and so we'll just keep watching this for a little bit. I'll probably do 1 or 2 more of these just so you can see how they behave. I actually have in your PowerPoint activity sheet a listing of what these histograms look like when we show them. So if you look ahead, you'll actually see the answer of what this next distribution is going to look like here. 80% done. %90 done. %95. Okay, it's pulled out all the samples. It's come up with 100,000 averages of 5 samples, 100,000 groups of 5, each group being an average. And it's recording those averages here. And so how common now will we have these extreme values at 0 and 100? It'll happen a little bit, but not very much now. I think you're going to find that things are more concentrated at the center right now. And as you can see, they are here. And the shape of the curve is becoming more curved, like a bell, more like the normal distribution here. So you can see here that just with 5 samples, we've gone from something that's flat to something that is a pyramid shape to now something that is a bell-shaped curve here. Okay, and you can see here that the mean is pretty much the same. It's about 50 here as well. The standard deviation's gotten even smaller, We're now close to about 13 or so for the standard deviation. It was around 20 last time. And I think for the first distribution, it was about 30 or so. Well, I can keep doing this for sample sizes that are larger here. Let me actually just try one more here. This will be 10, a sample size of 10, and we'll see here just what happens. So how many samples am I totally pulling out here? So it turns out it's 1 million. So 100,000 groups of 10, 100,000 times 10, 1 million. So it's pretty certain that we're pulling out some more than once. Again, that's okay. We're just trying to see how samples behave with this large population here. But once this is done here, notice with this previous distribution, we actually had some instances of things that never happened, 0 and 0 here. So it's possible for some things, for these things to happen, but it's so rare that with 100,000 tries here, you'll never see these things, happening usually. Okay, 33% done. Hopefully the resolution on the screen here is enough that you can actually see this, to see what's happening here. Okay, 50,000. $65,000. So remember, in previous runs here, the mean has pretty much remained at 50. The standard deviation has always gotten a little smaller. I think we're going to see that again here. Right now, the standard deviation is at a little over 13. So we'll see how it changes here with this latest run here with a sample size of 10. Okay, 92% done. All right, it's finished there. Now it's recording all of its results. So it's actually this column L here to the left. It's filling in top to bottom all 100,000 of those averages. So it's got to fill in a lot of data values pretty quickly here. But once it's done with that, now it's filling in the histogram here. But now it's going to plot it when it's done with that. And as you can see, we have a thinner distribution here and a smaller standard deviation to match it. The standard deviation now is just about 9.2. And so that pretty much is consistent with the fact that this is a more narrow curve and even more normal distribution shaped than before here. All right here, so I'll just show you, this is what it looked like in a previous run that just showed a sample size of 1. That's the flat distribution that we saw beforehand. Here's what the mean was. The standard deviation was about 30 for a sample size of 2. Remember this, we had that pyramid-shaped distribution with the same mean pretty much. Standard deviation no longer 30 but 20. For a sample size of 5, you saw this. It now started to look like a bell with a mean still of 50, a standard deviation of 13, sample size of 10, same mean, standard deviation of 9. For 20, the mean stays the same, standard deviation is about 6.5. For 50, standard deviation is now just a little over 4. 100, starting to get really skinny here with that standard deviation now going down to about 2.9. Sample size of 200, standard deviation is just a little above 2 right now. Tiny, very, very thin distribution here. Sample size of 500. So imagine averaging 500 data values together here. How often would you get an average of 1 or 2? Not very often. You'd have to have a bunch of data values that are, 500 data values that are all within the 1 or 2 range here, and that doesn't happen very often at all. Most of the time, when you're finding these averages here, you're finding them pretty close to 50. In other words, the center of, the actual close to the actual population average. So you can see here the standard deviation is getting smaller, 1.3 or so. Sample size of 1,000, getting even more skinny. Standard deviation's now dropped below 1. 2,000, even more skinny. Standard deviation's now about 2/3. 5,000, skinnier yet. Standard deviation's now below 1/2. And lastly, 10,000. This is a very, very skinny distribution here with a standard deviation of about 0.3. All right, so the point here is that as we increase the sample size, what happens to the mean? What happens to the sample mean here, the mean of all the samples here? They're pretty much staying the same here at around 50 or so. But what's happening to the standard deviation? Well, I think what you saw very clearly was that it starts out rather large, and as the sample size gets larger and larger and larger, then the standard deviation gets smaller and smaller and smaller here. So as the sample size gets bigger, the mean stays the same and the standard deviation goes down. This also means that sample errors go down because we're able to get pretty close to we're able to get closer and closer and closer estimations of that population mean. If you're sampling more and more data, then you're getting an answer that's getting closer and closer and closer to that population mean. And so estimates of the mean are more certain for large samples. Which would you trust more? A sample that only had 20 people in it, or a sample that had 3,000 in it? If they were trying to find out let's say the average resting heart rate for people, which would you trust more? The sample of 3,000 people, obviously, because we know that the more that the larger the sample size here, that means that those sample errors, in other words, how far away from the real value you are, gets smaller and smaller and smaller. And that's really what we saw as those distributions got skinnier and skinnier and skinnier here. Our certainty is getting stronger and stronger and stronger. So estimates of the mean are more certain for larger samples. And the increase in certainty here actually goes up in a very well understood way here. Notice if I take this sigma value here for the standard deviation and I divide this by the square root of this. Well, the square root of 1 is just 1, so right now this is going to be the same as that. But for this number here, I'm going to take this same number here and divide it by the square root of 2, and look at what I get here. For this number here, I'm going to take the original standard deviation once again, but now I'm going to divide it by the square root of 3, and look at what I get. Something very, very close to this. Taking this, dividing it by the square root of 10, I get this number here. This divided by the square root of 20 gets this number here. This divided by the square root of 50 gets me this number, and so on. So if you notice here, if I just take the original standard deviation and I divide it by the square root of n, the square root of the sample size here, then I get a number that's really, really close to the standard deviation for the distribution of the means. This is one aspect of the central limit theorem here. If I take these points here, these points are what we found out with our simulation here, and this line shows this function here that takes this original standard deviation and divides it by the square root of n and just keeps filling in everything here. You can see this line pretty much goes right over all of these points. So this describes something that happens in the real world here. So as the sample size gets larger, the standard deviation gets the standard deviation of the distribution of those samples of those sample means gets smaller and smaller and smaller, and gets smaller and smaller and smaller by a well understood quantity. You take it the original standard deviation, and you divide it by the square root of n, the square root of the sample size, and you're going to get this new standard deviation for these sample means. So these new standard deviations here are actually not called standard deviations, they're called standard errors. The standard error of the mean, notice we've got this little mean subscript here, it's just the same thing as the standard deviation, but we're dividing it by the square root of n here. So this is the thing that describes what is the standard deviation of the distribution of sample means. Here's a little GIF that I was able to get off the internet here that also explains this pretty well. You're seeing here two distributions of data here. They're actually exactly the same here. In this case, we're pulling off 5 values here and we're averaging them. In this case, we're pulling off 25 values here and then we're averaging those. And so you can see here just a few, each sample size is about 5 data blocks here, and after averaging them, then it places it into the appropriate slot here in the histogram. Same thing here, you can see there's more blocks here that are being sampled out of this, 25 to be sure, and then once those things are averaged, then an appropriate block is filled in here. You can watch these two histograms rise as all those samplings are done, but most importantly, watch the difference here in these two distributions here. Which one's skinnier, which one's shorter and fatter? In other words, which one has the smaller standard deviation? It's going to be this one, because for this one we're taking the original standard deviation, dividing it by the square root of 25 instead of just the square root of 5. So we're dividing this by a larger number, which means that our standard deviation of this distribution here is going to be smaller, which means also that our standard error is going to be smaller. So distribution of raw test scores, this shows the original standard deviation here. Here's the sampled raw test scores right in here, and here's the distribution of sample means, showing standard error sigma sub x. So this, again, the standard error is the standard deviation of these emergent distributions here of sample means. As you can see, this standard error changes with the sample size here. The standard error gets smaller and smaller and smaller the larger the sample size is. All right, so let's talk about this here. We actually saw this same thing here with our values here, that as the sample size n increases without limit, the shape of the distribution of the sample means taken with replacement from a population with mean mu and standard deviation sigma will approach a normal distribution here. So not only do we watch the sigmas get smaller and smaller and smaller here, but notice how the shape of the distribution changed here as well. We started off with something that was flat, certainly not a normal distribution here, and that's kind of an important thing that I don't think I've emphasized enough here. That I've talked a lot about the normal distribution and how it can represent a lot of data sets here, but you know just as well as I do that in the real world, not everything is representable as a normal distribution. Not all data sets look like this nice little bell curve here. Some are skewed, some are bimodal, some have really strange shapes to them whatsoever. But notice that even if we take something that starts off looking very not normal, not bell curved shape, but as we start to take multiple samples out of it and average those together, notice what happens here. We start to get more and more a shape that is bell-shaped. This plus what we're talking about a moment ago is the central limit theorem. So as the sample size n increases without limit, the shape of the distribution of the sample means will approach a normal distribution. So the distribution of the sample means will approach a normal distribution. As previously shown, this distribution will have a mean mu and a standard deviation sigma divided by the square root of n. So once again, if we take a distribution of the sample means from a population with mean mu and standard deviation sigma, then as the sample size n increases, the shape of the distribution of the sample means will approach a normal distribution here. I'm just trying to make it so that this is less a mouthful. As previously shown, this distribution will have a mean mu and a standard deviation sigma divided by the square root of n here. So there's actually two things to talk about here. One is how the shape of the distribution changes, the larger the sample size, and also how more compact the distribution gets with increases in sample size. Here's another example of this here. I'm going to have to remove myself from the screen here in just a moment. But here's what the original shape of the data looks like here. There's just they just pull out some data set that has a lot of stuff that's very, very small, a lot of stuff that's very, very large. And this is what the original data set looks like. It's not normal whatsoever. It has nothing, this looks nothing like a bell-shaped curve. It doesn't even have just one mode. It's got two modes, doesn't it? So one on either end of the data. So it's definitely, it's not even symmetric that way. So it's not symmetric, it's not unimodal. This thing does not look at all like a bell-shaped curve. But if we start taking samples of this data set here, samples of size 2, well, sometimes we're getting one of these small ones and these large ones that are being averaged together, so we're getting a lot of samples, a lot of sample averages that are now in the middle now. If we start taking samples of size 3, we get a bunch of peaks here, samples of size 4, more peaks still, 5, 6, 7, 8, 9, 10, 11. Look what's starting to happen here as the sample size gets larger and larger and larger. And here it's getting up to 64, 128, 256, and 512. You can see even long before that, we're getting a distribution that's getting more and more normal shaped here. Let me get my screen out of the way there so you can see this. The larger the sample size, the more bell-shaped, the more normal that this distribution looks. So regardless of the shape of the original distribution, with larger and larger sample size, the distribution gets more and more normal. Now, just as you can compare individual samples with the distribution of sample values, you did this when you were calculating z-scores. You were taking just an individual sample value, comparing it with the mean to see if it was bigger or smaller. If it was smaller than the mean, you get something negative up here. If it was larger than the mean, you get something positive up here. And you divided that departure from the mean by the standard deviation. And in doing so, got a z-value. You can do that with individual samples. You can also do that with individual sample means, with that same distribution of sample means here. So instead of x, this becomes the average of x. That's the sample average of x subtracted from mu. And instead of the standard deviation here, we now have the standard error of x bar, the sample mean of x. So when the original value is normally distributed, the distribution of the sample means will also be normally distributed for any sample size n. When the distribution of the original variable is not normal, a sample size of about 30 or more is needed. That's a round figure that we use here. When the sample size gets to be around 30 or so, then we say, yeah, this is a distribution here, the sample mean distribution that's really starting to look more and more like a normal distribution here. And so we can then use a normal distribution to describe the distribution of the sample means. The larger the sample, the better that approximation will be. So here's an example here. A.C. Nielsen reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. Assume the variable is normally distributed. See, now you kind of know why that language has been included in a lot of these problems that you've had before. It's not always true that these variables, these data, are distributed like a normal distribution. But here we're being asked to assume that that's true. The variable is normally distributed, and the standard deviation is 3 hours. So if 20 children, 20 children. We're not dealing with individual children, are we? We're dealing with a sample of 20 children. If 20 children between the ages of 2 and 5 are randomly selected find the probability that the mean, the sample mean of those 20 children, find the probability that that sample mean of the number of hours they watch television will be greater than 26.3 hours. Okay, so how do we do this here? Well, first of all, we're not dealing with the standard deviation any longer. We're dealing with the standard error. So we have to do that sigma over the square root of n thing now, because we're now not just dealing with a single child, we're dealing with 20 children here. So we have to take our standard deviation and divide it by the square root of 20. So our standard error of the mean is going to be 0.671. And we'll use that for our standard deviation when we're calculating our z-value, not the 3 hours. We're going to be using this. So you can see that here. Okay, so what is the average that we're given here? Okay, 26.3 hours. We want to see how far that is from the value of 25 in terms of standard errors of the mean. 26.3 minus 25, it's going to be something positive on top here. How positive? Well, we're dividing it by the standard error to give us 1.94. Okay, 1.94. Guess where we're going to go? We're going to go to our familiar normal distribution chart that I've given to you here. But keep in mind, let's see, find the probability that the mean of the number of hours they watch television will be greater than 26.3 hours. So we're wanting to find out what's the probability that this z-value will be larger than 1.94. And that means I have to take the complement of this probability, 1 minus p, the probability that z is less than 1.94, which means that I'm taking 1 minus 0.9738, this is from the chart, and I get 0.0262. So in other words, it's about a 2.5% probability that the number of hours, the average number of hours of 20 children will be larger than 26.3 hours. All right, so work on this one yourself. The average time spent by construction workers who work on weekends is 7.93 hours. It's a little over, that's over both days of the weekend here. Assume that the distribution is approximately normal and has a standard deviation of 0.8 hours here. So find the probability that an individual, we're not dealing with means here, find the probability that an individual who works at that trade works fewer than 7.5 hours on the weekend. And then, if a sample of 40 construction workers is randomly selected, find the probability that the mean of the sample will be less than, again, 7.5 hours. You're going to get different answers for these two things here. One is our old method, the other one is our new method. Take some time for this. Welcome back. Well, I really like this problem actually because it allows you to take a look at the same threshold, that is 7.5 hours here, and just take a look at it from two different perspectives here. One is the perspective of how unusual is it to find an individual who works fewer than 7.5 hours on the weekend versus how unusual is it to find 40 constructive workers whose average number of hours worked is less than 7.5 hours. That's going to happen far less often just because of how widely distributed these things are. And so you can see that happen here. We have two instances in which we are calculating a z-value here. And for both instances, the numerators are exactly the same. The mean is the same. The threshold of 7.5 is the same. But what's different? Here, the standard deviation is used, and here, the standard error of the mean is used. And that gives you some very different results here. Negative 0.54 means that you're about 1/2 of a standard deviation away from the mean, but here 3.4 means that you're about 3.5 standard deviations from the mean. And so the chances of finding somebody who works less than 7.5 hours on the weekend is just under 30%, but the chances of finding somebody, finding 40 people whose average work over the weekend is 7.5 hours, that is about 0.03 of 1%. So you can see that's very, very different when you're working with averages. It's a lot more difficult to find extreme cases when you're averaging all those things together. Hence, the standard error is used, which is always smaller than the standard deviation. All right, here's a second one to work on here. The average drive to work is 9.6 miles. Assume the standard deviation is 1.8 miles. If a random sample of 36 employed people who drive to work are selected, it's not going to happen too much right now, but nevertheless, 36 employed people who drive to work are selected. Find the probability that the mean of those 36 people, the mean of the sample miles driven to work, is between 9 and 10 miles. So remember, you're going to be calculating two different z-values, and you're going to find the area in between the two here. So take some time for this one. Welcome back. Well, there's much in this problem that should have been familiar to you, not only from what we've been discussing today, but from previous days here. If we take a look at what's the way this problem actually ended up here, let me move myself from the screen here. We had two thresholds to work with in which we had to calculate some z values, and then to find the area in between them, we had to take one probability and subtract the other one, getting that area in between here. The only thing that really was added to this whole process here was where we had to adjust the standard deviation that we were dividing things by dividing it by the square root of n here, dealing with the fact that we're not dealing with individuals, we're dealing with groups of 36 people, and we're not dealing with individual data values, we're dealing with averages here. So after calculating this, everything else really proceeded in ways that we've been talking about in earlier class periods. Okay, so to summarize all that we've discussed here today from the central limit theorem, think back to what we've been discussing here. Do you know, first of all, how distributions of sample means change when sample sizes get large? How does the shape change? Does it gets more and more what? Number two, how do the standard errors change as sample size get larger? Do they get bigger? Do they get smaller? Do they stay the same? Also, what happens to the sample mean as the sample size gets larger? Does it get bigger? Does it get smaller? Does it stay the same? And lastly, do you know how to calculate these z-values and probabilities from distributions of sample means? What's the extra steps that you have to take in order to be able to calculate those new z-values dealing not with individuals, but with sample means? Well, that's essentially everything that we've discovered here, and this is actually finishing up our chapter on the normal distribution. I'll see you next time.